Section 13.7, Polar, Cylindrical, and Spherical Coordinates. First, we discuss the polar coordinates, which we already know from pre-calculus. Then we discuss cylindrical coordinates, which is very similar to polar. And then a little bit differently, it would be spherical coordinates, and we discuss that one later. Polar and Cartesian coordinates. We usually use Cartesian coordinates x and y to present a point in a plane. However, polar coordinates r and theta are very convenient when you're dealing with circles, arcs, and specific type of curves, spirals, and so on. What is the polar coordinate? So if you have x and y on the plane, you want to find the r and theta such that r is the distance of the point from the origin, and then theta is the angle that a line segment connecting that point to origin makes with the x-axis. And theta is measured counterclockwise. Is representation, the polar representation of a point, unique? No. You can also assume that r is negative and then replace theta by theta plus pi. You can also other ways, any r and theta is also equal to r and theta plus. So r and theta can be also equal to r and theta plus 2 pi, and so on and so forth. So and it's not the unique representation, but for purpose of calculus 3, we're after this section is over, we always assume theta is between 0 and pi, and we assume r is positive. Let's do a few examples of polar and the conversion of polar and Cartesian coordinates. So let's plot the point given in the polar coordinates. First one is 1 and pi fourth. So how do we do it? We find the angle and the ray that makes pi fourth. Then on that one you basically separate 1. So this is 1, and then that would be the point 1 and pi fourth. What about -1 and pi fourth? So with -1 and pi fourth, you basically add pi to pi fourth. It's over here. Again, you separate 1 from the origin, and this one is the point. So here and here. How about 7 pi fourth? 7 pi fourth is basically over here, and separate 1 out of it, and it's right there. How about negative pi fourth? 1 and negative pi fourth. Negative pi fourth, again, the same thing as 7 pi fourth, and you separate 1, it's right there. So basically, you're using the, because all of the radii are 1, you're using a circle of radius 1, and those radii of the radii that separate the thetas, theta equal to pi half, theta equal to 3 pi half, theta equal to 5 pi half, and so on and so forth, and then you find the points. So these two are P1 and P2, then P3 is right here, and P4 is going to be the same thing as P3. So I talked about radii that signify theta, and I talked about circles that signify the radius of the point. And so these make the polar grid on your plane. And so you basically use these pieces of lines that make the thetas for the signify the theta for you, and then you use the circles to signify different radius or different r's, and that makes the grid on the plane for you. So far we've basically tried to graph points in polar coordinates, and from there we kind of got an idea on how the Cartesian values of the point or Cartesian coordinates will look like. And so let's write this out. If x and y is the Cartesian coordinate, and r and theta is the polar coordinate for a point P, and then notice here this is r, and this is theta, and this is y, and this is x. So there's a triangle in there, and basically sine of theta is equal to y over r, cosine of theta is equal to x over r, and from there I can say y is equal to r cosine theta, r sine theta, sine theta, and x is equal to r cosine theta. And this is actually a formula that you can use to convert polar to Cartesian coordinates. If I give you polar right here, you can get the Cartesian values over there. So these are the input, outputs are x and y. How about the other way around? So the other way around, if I want to find if I have the Cartesian and I want to find the polar, and basically r squared is equal to x squared plus y squared, so r is the square root of basically r is going to be square root of x squared plus y squared, right? And that is coming from this triangle, because this was x, that was y, that was r, and so and this is a right triangle, so it's going to be x squared plus y squared equal to r squared. Now how about the theta? And so what you can see is theta, and theta is the tangent of theta is y over x. So you can use arctan, and you have to be careful, because when you use arctan, only returns to you thetas that are between negative pi half to pi half. So if you are not in that area, which means that if x is not positive, when you're using arctan, you have to consider that and add a pi, basically. Pi or pi plus 2 pi, depending on. But in this course, we are trying to stay for theta to stay between 0 and 2 pi. Cylindrical coordinates in 3 space. So the cylindrical coordinate of a point P in 3 space are coordinates of point P in 3 space are R and theta and Z. So if you take point in Cartesian 3 space x, y, z, and you want to convert it to r theta z, the z stays the same. Then you basically drop a perpendicular from the point P onto xy plane, and then find the polar coordinate for that point on the xy plane. That would make r and theta. So r and theta are the polar coordinates of the projection of P onto the xy plane. Z is the same as in Cartesian coordinates. In cylindrical coordinates, we usually assume r is bigger than equal to 0. So this is we're starting to get to the point that we're assuming r is bigger than 0, bigger than equal to 0. So the conversion between cylindrical and Cartesian is very similar to the conversion between polar and Cartesian. So converting, if you're converting from cylindrical coordinates to Cartesian coordinates, x again is r cosine theta, y is r sine theta, and z is z. And if you're converting from Cartesian to cylindrical, r squared is x squared plus y squared, and tangent theta is y over x, and z is equal to z again. Example, convert the cylindrical coordinates, a cylindrical point r and theta and z into r theta and z equal to 2 and negative pi fourth and 1 to Cartesian coordinates. So r is 2, theta is negative pi fourth, and z is equal to 1. Z stays the same. To find x, you use r cosine theta, and to find y, you use r sine theta. So 2 cosine of negative pi fourth is square root of 2. 2 sine of negative pi fourth is negative square root of 2. And the Cartesian coordinates is going to be square root of 2, negative square root of 2, and 1. Let's convert the other way around. Let's convert the Cartesian point x, y, z equal to negative 2 square root of 3 and 1 to cylindrical coordinates. Z is going to stay the same. Z is going to be 1. To find r, negative 1 to power 2 plus 2 square root of 3 to power 2 is going to be r squared. And tangent of theta is going to be 2 square root of 2, 2 square root of 3 over negative 2, which is negative square root of 3. So r is 4, and tangent of theta is equal to negative square root of 3. And so what I know of, to find theta itself, you have to know a little bit more knowledge. And from here, I know that x is a negative value. So what I find for by plugging in this, by using arctan, I find negative pi third. And so I have to add pi third to get theta equal to 2 pi third for the angle. So 4, 2 pi third, and 1 are the is the cylindrical point. Now describe this, another example. Example 4, describe the surface given by the equation in cylindrical coordinate, and the equation is z equal to square root of r squared plus c squared. So how do we, we are familiar with the Cartesian. From look of this looks like a quadric surface, but we're familiar with the Cartesian quadric surfaces. So let's see if I can convert. So this is going to be still z. R squared is going to be x squared plus y squared plus c squared. Again, this seems like to be part of a quadric surface because it's only positive here. Let's go to power 2 anyway to recognize this a little better. Put these two together, take the other one to the other side. So from here, I know that z squared has to be bigger than c squared. And this is one of those 3 quadric surfaces between a cone, elliptical, hyperboloid, and of one hyperboloid of one sheet or hyperboloid of 2 sheets, and which one it is. And so since there, for some z values, there's no x and y value, it's hyperboloid of 2 sheets. And so, but it's hyperboloid of 2 sheets, but again, you see that there's only positive in here. When you go to power 2, you actually, the hyperboloid of 2 sheets has 2 sheets, but we only use the upper part. So this is upper piece of the hyperboloid of 2 sheets, and the original equation only describes the top sheet. And the bottom sheet would have been z equal to negative square root of r squared plus z squared. And so this is the picture again, and you can see that this is the top part is this equation, and the bottom part is this equation. Example 6. Describe the solid region shown below using inequalities in cylindrical coordinates. It's cylindrical coordinates, so it makes sense that we describe cylinders using cylindrical coordinates. And actually, it's not quite unrelated. A lot of times when you see cylinders, you tend to use cylindrical coordinates. So in here, what I see is cylindrical coordinates has 3 coordinates, right? Here I see the bottom part is z equal to 0, the top part z is equal to 3. So z for this one is between 0 and 3. Also for that one. Now, what else do we know? And here it goes all the way around. So theta does 1 full round. Theta is between 0 and 2 pi. But how about the other one? Is this 0 to 2 pi? No, theta it actually sort of starts from over here, which is negative y value, and goes all the way to pi half, which is right here. And so this one is negative pi half for theta. So theta is between pi half, and negative pi half. For this one, r is, so in here r goes, and when you're inside the cylinder, r is less than 2, but when you're on the boundary of the cylinder, r is equal to 2. So r is between 0 and 2. And here also 0 and 2. Again, r when you're inside the cylinder, let's say in this point, r is definitely less than 2. But on the boundaries of the cylinder out here, r is equal to 2. So this is actually a good exercise, and you can practice on it to realize how the cylindrical coordinates they work. All right. Like question 13.7a. What are the cylindrical coordinates of the point x, y, z equal to 3, 3, and 7? So turn off the, let's pause the video and solve. Hopefully you pause the video and now you're back. So first thing is you have to find r, theta, and z. This one is z. And now how do I find x and y? X, I have to use r. Oh, I'm sorry. How do I find r and theta? R is going to be square root of x squared plus y squared, and x squared plus y squared is going to be square root of 18, which is 3 square root of 2. Now, what is theta? Theta is going to be, so tangent of theta tan of theta is going to be y over x, which is 3 over 3, which is 1. And theta is in the first octant. And the point is in the first octant. So theta is going to be pi fourth. So 3 square root of 3, pi fourth, and 7. C is the answer. I click error 13.7b. Which of the following sets of inequality describe the portion of cylinder of height 4 and radius 3 above the third quadrant of the XY plane? So give yourself a minute and come back. So hopefully you solved it. A cylinder of height 4, that means z is between 0 and 4. So basically this one's out. Radius is 3. Therefore r has to be between 0 and 3. And so this one is out because r, and we're considering everything inside the cylinder. And then it says above the third quadrant of XY plane. Where is the third quadrant? And this is the third quadrant. And so this starts from pi and goes to 3 pi half. So B is the answer.